All right, so now we're going to talk about Bayesian inference in this series of videos. And remember that Bayesian inference is a way of thinking about the world, a way of understanding how do we take our data and reason about some quantity in the world that we want to know. And it involves a particular way of thinking about the problem, and that results in a particular way of sequence of steps that we'll use to solve the problem. And so in this series of videos, we'll kind of get a sense of how do we set up the problems, like what is prior, posterior, what does all that mean, and how do we actually do some like calculations and manipulations with those and use those to actually get something meaningful out at the end. So if you remember, our setup is that we have some hidden state of the world that we call theta. And maybe theta is the true fraction of people in a population who are going to vote for a particular candidate. Maybe theta is the underlying concentration of some particular compound in a biological assay. Maybe it's the true state of a social media account, maybe a social media account, maybe a bot or not a bot, and all we get to observe are the posts, and we have to infer, is that account an actual human or not, right? So it reflects some hidden thing about the world that we care about, that we're interested in, but we can't see directly. Instead, what we get to see is X. And the reason this is interesting is because X and theta are related, right? If you see the posts that an account makes on social media, you get some idea of whether or not they might be a bot, right? Similarly, if you go out and poll people, you get some idea of what the true fraction of people who vote for a candidate might be. So this is why we set up the problem this way. We link the data we get to the hidden thing that we actually want. And Bayesian inference provides a way of taking the data X and reasoning about theta. Some pros are, one, it lets you fold in some like prior knowledge you have about theta. And two, it lets you reason not just about like one single theta that you get out at the end, but instead it gives you an entire distribution of theta. It tells you, well, here are the different possible thetas you get. Here's how likely each one is. And you can then take that and say, well, I want the most likely one, or I want the average, or whatever you may be interested in. And so this is kind of the setup for Bayesian inference. In the next few videos, we're going to go into more details on this. All right, so in this sequence of videos, we're going to use a particular example to make the ideas behind Bayesian inference a little more concrete. So we're going to walk through how you set up a problem, how you do some computations, and so on. And the example we're going to use is, let's say that you're out shopping online, of course, and you're interested in buying maybe an air purifier. Maybe you live in California, you're worried about wildfire smoke, and you want to buy an air purifier. So you look and you see two that really pop out. They're kind of in your budget, but they have different reviews. One seems to have fewer, but like more positive reviews. One has more, but like there's a negative review. And you want to know, well, which one is better, right? So let's make this a little more concrete. So let's say that we have, so air purifier number one has, let's say that it has 5 positive reviews and 0 negative reviews. Right, so it's all positive, but there aren't that many reviews. Whereas air purifier number 2, let's say that it has, I don't know, let's say 19 positive reviews and 1 negative review. So notice here that I'm already kind of simplifying things, right? You know that when you go and look at reviews on e-commerce sites, they're usually like number of stars, but here I'm already simplifying to like positive or negative, thumbs up or thumbs down. And there are already places that do that, right? Like if you think about rating things on Netflix, it asks you for thumbs up, thumbs down, instead of star rating. So let's say that you go out and you see these 2 air purifiers, and I want you to pause for a sec and think about which one of these 2 you're more likely to buy if you see this right now. Okay, so whichever one you think you'll buy, I probably look at this and I'd probably want to say, well, I think I'll buy number 2. It has more reviews, even though one of them is negative. Like 19 versus 5 seems better. So let's kind of formulate a Bayesian inference problem around this task. So what we really want is you want to know, how good is the air purifier? How good is number 1 and how good is number 2? And we want to relate the data we get about the reviews to this like inherent goodness of the air purifier. How like high quality is it, reliable, and so on. So we're going to come up with a number that quantifies how good the air purifier is. And we're going to call that number theta. right? So remember that in Bayesian inference, in these inference setups, we say theta is the hidden state of the world. So theta is going to be, theta 1 is going to be the goodness of air purifier 1, and theta 2 is going to be the goodness of air purifier 2, right? So what does this mean, like the goodness? Well, let's make this even more concrete and say, I'm going to say that theta is a number between 0 and 1. That is the probability that somebody will leave a positive review on that, or the probability that a particular review that somebody leaves will be positive. So this is the probability that reviews are positive. Now, this doesn't capture everything about how good the air purifier is, right? It doesn't capture like how fast it like changes the air, how often you need to replace the filter, how energy efficient it is. This is just one simplified way of measuring how good it is based on how many reviews it gets. So we have these thetas, they're 0 to 1, and we're thinking of them as the probabilities. And then our data X is going to be the actual reviews themselves. And we're going to say they're either positive or negative, right? So we're going to say that if they're positive, we're going to call that a 1. And if they're negative, we're going to call that a 0. And now we want to put some kind of random model over this whole setup, right? We already know that, well, we've seen random variables like this before, right? Like they can either be 1 or 0. And so we know like a good choice of distribution for that is Bernoulli, right? We know that with some probability they're 1, with some probability they're 0. So we're going to say that the probability of X, well, we need to know like that probability, right? And that probability is the theta. So probability of X given theta. So if we know like how good the air purifier is, what like the probability that it'll generate a positive review, if we know theta, then we can say, well, the probability of getting a particular X is theta if X equals 1, and it's 1 minus theta if X equals 0. But this is kind of cumbersome to like, carry around this like, 2 different cases the whole time. And so we're going to play a little trick, and we're going to write this as theta to the power of X, 1 minus theta to the power of 1 minus X. And I want you to take a second and convince yourself that these two are exactly the same. Plug in X equals 1. You see that this first term is theta. The second term is, the first term is theta. The second term becomes just 1. So you get theta. Plug in X equals 0. The first term goes away. Second term becomes 1 minus theta to the power of 1. So you get 1 minus theta. Okay, so this thing here is called, this P of X given theta is called our likelihood. So it relates the probability of getting the data that you got to the hidden state of the world that you're interested in. All right, so now we're going to continue talking about this model that we set up before, right? And we're going to say, okay, we have this idea of a likelihood function that connects our X and our theta, but we want to make things a little more concrete, right? Again, like let's like really get down to the nitty gritty of like, okay, so this is like in likelihood, but what does it actually mean for the data I got, right? Like I got for the first air purifier 5 positive reviews and 0 negative reviews. What does that tell me about what I should think theta actually is? Is it like 0.1, 0.7? What should I actually think it is? So what we need then is we need a way to say, okay, this is the probability for one particular review, but what is the probability of all the reviews? And let's just focus on air purifier number 1 for now. 1 only. So we'll just look at theta 1. And what we'll say is that probability, what we really want is probability of X1, X2, X3, X4, X5, right? Because we got 5 reviews and we want that distribution given theta. And let's stop and talk about what this means, this like P of X is given theta. What this means is this is a probability distribution over values of X given a particular theta. So it says you plug in the X's that you actually got into this function and it'll tell you what the probability was, right? That's how a likelihood function works. You give it a parameter, the theta, and you give it some particular values that it got, and it spits out a probability, right? Well, either a probability or a probability density. In this case, it's a probability. And so this is not just like, the probability of getting ones. We're writing this function out in the most general case where like we don't know what the x's are, and we're just setting up this function. Okay, so what is this probability? Well, we're going to make an assumption here. We're going to say that if we know theta, then the reviews are all independent. So obviously the reviews are not all independent, right? Like a good air purifier is going to have more positive reviews. The bad one's going to have more negative reviews. But if you know how good the air purifier is, maybe it kind of makes a little more sense to assume that they're independent. Still doesn't make total sense. You can imagine like people see more positive reviews, so they're more likely to leave one. There's like astroturfing, people can like collude to like leave positive reviews and so on. But we're just going to assume that they're independent. So we're going to assume that this is equal to probability of x1 given theta times probability of x2 given theta, and so on. And we're just going to multiply all the way up to probability of x5 given theta. So what happens when we take this formula here and we multiply 5 versions of it for x1, x2, x3, x4, x5, and multiply them all together? Well, what we get is we get theta to the x1 times 1 minus theta to the 1 minus x1 times theta to the x2, 1 minus theta to the 1 minus x2, and so on, and so on. And when we multiply all of these things together, we see that the exponents just add, right? We can take all the terms that have thetas. We can take this term, and so on, the term for x3 and so on. We can just like take them and add all their exponents together. And we can take this term, and all the ones 1 minus thetas and add all their exponents together, right? So what this is actually equal to is it's theta to the x1 plus x2 all the way up to x5 times 1 minus theta to the 1 minus x2 plus 1 minus x1 plus ... plus 1 minus x5. And so we can simplify this a little further and say this is actually just theta to the number of positive reviews times 1 minus theta to the number of negative reviews, right? So this is a simplified way of writing out the probability of getting all of these, any particular set of x's given theta is just equal to theta to the power of however many positives you got times 1 minus theta to the power of however many negatives you got. Okay, so this is our likelihood function, right? This tells us what is the probability of getting some particular set of x's given the parameter theta. All right, so far we've kind of talked about like, how do we get, if we know theta, then like, how do we find the probability of x? But that's not the thing I actually care about. What I actually care about is I get a bunch of x's and I want to know theta. I want to know how good is the air purifier if I got, 5 positive reviews, or how good is the air purifier if I got 19 positive and 1 negative reviews. So what I want is a procedure that takes me from x's to thetas, right? It takes me from the data to the hidden state of the world. And I know I said that today is going to be all about Bayesian inference, but I lied. We're actually going to start with a frequentist approach called maximum likelihood estimation, and MLE for short. So what MLE does is it says that we have this likelihood function, right? This thing up here is our likelihood, and we're going to find the value of theta that makes that as big as possible. Why does that make sense to do? Well, let's take 2 like simple examples here. Suppose that I said, well, what if theta like 0.001? Then the probability of getting 5 positive reviews from theta being 0.01 seems really low, right? So like the likelihood is really low for this like bad theta 0.01, right? And like if you say 5 positive reviews, like really bad air purifier, that doesn't make sense. Now, what if I say, well, maybe theta is like 0.99? In that case, what is the likelihood? Well, the likelihood is pretty high, right? Like the likelihood of getting 5 positive reviews if theta is 0.99, pretty high, right? So this idea of maximizing the likelihood is like a good place to start. Seems pretty reasonable, right? We want to maximize the probability of getting the thing we got, right? So we want to find the parameter, this hidden state of the world that makes the thing we got as likely as possible. And so the way that we set this up is we write theta equals argmax over all possible thetas, p of x1, so on, given theta, right? In this case, there's 5 x's, so this is like x1 to x5. In general, this is like the probability of observing all your data. So one trick that people commonly play is, you notice a lot of probability distributions, including these ones and like others you've seen, like the Gaussian, the normal density, tend to have a lot of like the interesting stuff going on in the exponent. And if the interesting stuff is going on in the exponent and you're multiplying things together and you want to maximize, it tends to make your life easier if you take the log. And the reason that I can do this is that log is a monotonic function, right? If you think about log, it's like constantly increasing, right? So if I find the value of theta that makes the likelihood as big as possible, that same value of theta will also make the log likelihood as big as possible. So we'll often play this trick where we'll call it max likelihood estimation, but in practice, it ends up being like max log likelihood estimation. But they're the same thing, right? Like it gives you the same value of theta, it's just the log is more convenient. Okay, so what is this p of x given theta? Well, this is equal to argmax over theta log of, and I'm just going to fill in this right here, because we said that is what the likelihood is, right? So this is log of theta to the number of positives in all the x's times 1 minus theta to the number of negatives. And, you know, if I were being like super mathematically precise, I'd write the number of positives as like a sum and all that, but you know what I mean when I say number positive, number negative. It's easier to read. I'm not being super, intense about the notation. Okay, so now we can see why the log helps us, right? Because we have this interesting stuff going on in the exponent, and the log basically turns that into, multiplication, and then multiplying these two terms together becomes an addition after we take the log. So this is equal to argmax over theta, number of positives times log theta, plus number of negatives times log of 1 minus theta. Great. So now we want to find the value of theta that makes this as big as possible. Well, how do we maximize stuff? The simplest way is take the derivative, set it equal to 0. And that's exactly what we're going to do. So this then becomes, we're going to take the derivative. So when we take the derivative of number of positives times log theta, then we get number of positives. So differentiate, set equals 0. And so the number of positives divided by theta, derivative of log theta is 1 over theta. And then here, this is number of negatives. And derivative of log 1 minus theta is 1 minus theta times negative 1, right? And I'm going to say instead of times negative 1, I'm going to turn this plus into a minus, right? And now I'm going to set the whole thing equal to 0. I can rearrange some terms, and I get theta times negative, well, I'll work out the algebra. So we'll say that number of positives over theta equals number of negatives over 1 minus theta. So this means that, and I'm just going to start calling this P. I'm going to start calling this N. So 1 minus theta times P equals theta times N. And if I keep going, I can see that I get P plus, P equals theta times N plus P, right? I'm bringing this term over to the other side, and behold, I get theta equals P over N plus P. So here's the thing we got. This is the theta that maximizes the likelihood. And does this make sense? Well, yeah, it does. It says that the theta that maximizes the likelihood is the number of positives divided by the total number of reviews. Totally makes sense, right? Like the more positives, the higher your theta. The more reviews, like the more you divide by it. So this is a very intuitive result. And you'll find that with a lot of MLE estimates is that the result ends up being fairly intuitive if you set your model up nicely. So this is the frequentist result. Now, notice that this doesn't take into account any information about, well, but like I know that like most products, are good, or maybe I think that like Amazon has a counterfeit problem. Maybe like most products on there are bad, right? Or maybe there's like some bimodal distribution. There's some information about theta that I know that I want to use, and that's what we'll use in Bayesian inference going forward. So quick recap, what did we do here? We did inference in a frequentist way, right? We thought about the likelihood, right? We thought about the likelihood P of all the x's given theta. And we found the value of theta that made it as big as possible. Now, with Bayesian inference, what we're going to do is we're going to compute. Instead, we're going to say, well, this assumes that theta is fixed. But I want to assume that theta is random. And so I'm going to actually compute what's called the posterior distribution over theta. So we'll do that in the next few videos.
Let me talk about an alternative, which is, okay, so the Bayesian approach. Okay, so in some sense, the Bayesian approach here is pretty natural because we care about theta at the end of the day. So what does that mean? That means what we kind of want is P of theta given x, right? So I want to know how likely is theta to take on different values given what I've observed about x. And there's one issue though, which is that I need some more information, right? Because how do I get P of theta given x? Well, by Bayes' rule, this is P of x given theta times P of theta over P of x. And let's be a little bit more precise because I have these 5 reviews, right? So this is P of theta given x1 through x5 is P of x1 through x5 given theta times P of theta over P of x1 through x5. This is the thing we already know, right? This is called the likelihood. So this is something we haven't specified yet. This is called the prior. So this is going to be our kind of prior beliefs about what theta is. And then this is what Mike called the posterior last time. And I don't think that Mike gave this a name. If he did, let me know. I'll put it in red because actually we're just not going to care about this one. Because if you think about it, this is a constant because it's the probability of the observed data. X1 through X5 are all fixed because we've already seen them. So this is just going to be some fixed constant. And it's going to be whatever constant makes everything add up to 1 because these things are probabilities. So we're actually just going to kind of ignore this. And we're going to write this in a slightly different way, which is that P of theta given x1 through x5 is proportional to. So this is a symbol that says is proportional to the likelihood times the prior. And so there's two things we're going to need to deal with here. So there's kind of two questions we have to deal with. So one is, what is the prior? But then there's a second thing, which is even if I know what the prior is, that doesn't tell me what decision I should make, because I'm still going to have some uncertainty about theta, even after I condition on my data. And so I also need something about how to actually make my decision, because I need to somehow turn this probability distribution over theta that I get into a decision at the end of the day. And so we'll talk about both of these two issues. But I'm going to focus on this first one to start with, and we'll try to understand how the prior actually kind of affects what we do here. Okay, so let's talk about the prior. So if I have a Bernoulli distribution like this distribution, there's actually a kind of natural prior to associate with it that tends to make the math work out nicely, at least. Does anyone remember what that might be? Like, what's the prior I often use if I have Bernoulli distributions? It also starts with a B. Yeah, so I saw beta, yeah. So an example prior, and again, this isn't necessarily saying this is a prior you should use, but it's at least a mathematically convenient family, and it has some nice properties. This is what's called a beta distribution. So in a beta distribution, we assume that the prior probability of theta is proportional to theta to the r minus 1 times 1 minus theta to the s minus 1 for some r and s greater than 0. And we call this a beta of r comma s distribution. So as an example, if I have beta of 1, 1, what's that distribution? What's beta of 1, 1 going to be? Yeah, so beta of 1, 1 will be uniform, right? Because it's going to be theta to the 1 minus 1, 1 minus theta to the 1 minus 1. That's just 1. So this is going to be uniform over the unit interval. But you can have sort of other things as well, right? If we have beta of 2 comma 1, we'll have a density that is just linearly increasing. So it'll just be theta beta of 1 comma 2 would be 1 minus theta. So this one sort of skews toward 1. This skews toward 0. And the reason why we like beta distributions is because they're what's called the conjugate prior of a Bernoulli. And what this means is that if I have a beta prior and I have a Bernoulli likelihood, I end up with a beta posterior. So just as an example, let's suppose that P of theta is this beta distribution. Then my posterior And let's do the posterior for the particular observations we had in mind. So let's suppose these are all equal to 1. Is going to be proportional to the likelihood times the prior. This likelihood is theta to the 5th. The prior is the Bernoulli. And so then this comes out to theta to the r plus 5 minus 1, 1 minus theta to the s minus 1, which is equal to beta of r plus 5 comma s. So the kind of reason why it's nice to have this beta distribution is because everything stays as a beta distribution. So we still need to understand how beta distributions behave, but that's why you might want this. And so I want to kind of give like a bit more intuition for what's going on here. So I have some Jupyter notebook demos just to kind of show you what this looks like graphically. So I'm going to stop sharing this screen. And I'm going to start sharing another screen. Let's see if I can get this to work. Can you see this? So actually, apparently, while I'm sharing this screen, I can't see the chat anymore. But are one of the GSIs here?
Yeah, we can see the screen share.
Great. And yeah, can you just monitor the chat while I'm doing this, since I won't be able to see it?
Okay, sure.
Okay, great. Okay, so I'll share this with you all after class, but this is a kind of Jupyter notebook that will plot different priors and posteriors for you. So actually, let's start with beta. So this is, the arguments here are, the first two arguments are the R and S values that we were just talking about for the beta distribution. And then these are the observations. So let's make this 5 and 0 for 5 positive and 0 negative. So you can kind of see what this looks like. So the prior is in yellow and the posterior is in blue. So this is saying, suppose we have this beta of 3, 2 prior. What's that kind of saying? That's saying, well, I think most of the thetas, so maybe we can think of this as like how positive, like most products tend to be like reasonably positive, but not super positive. Like maybe the positive probability is somewhere between 50% and 80%. But there's a lot of uncertainty. And then, oops, I mixed up arguments. Wait, okay, I really mixed these up. Sorry, one sec. What are the actual arguments? Oh, okay. Sorry, this is the total and the number of positive. There we go. Okay. So this is saying we see 5 reviews total and 5 of them are positive. So if you had that as your prior, that most things are like generally pretty positive, then once I see 5 positive things, now I think it's like fairly likely to be fairly positive, although not that likely to be like super positive, because I have kind of this low probability on things being super positive or super negative. So that's what things would look like if you had this kind of beta of 3, 2 prior. let's take a simpler prior of just a uniform distribution. Then since you haven't really excluded very positive cases, you actually place a lot of probability towards that end, but you still have some uncertainty. And if I had to take like the mean, it would probably be kind of like near maybe like 0.9-ish or 0.95-ish. And you can sort of play around with different things, right? So let's suppose I did a beta of 100 prior. Then that says that I'm super confident that things have close to 50% positive reviews as my prior. And so even after I see 5 more positive reviews, I'm still going to be pretty confident. And so I'm not going to move much. And you can sort of think of the parameters of the beta distribution as sort of pseudo observations, where I'm sort of pretending like I've so far observed 100 positive reviews and 100 negative reviews. And so if I observe 5 more positive reviews, that doesn't change things too much. What do you think will happen if instead I made it beta of 100,1? So let's see. Okay, so now I'm just like super, super confident that it's going to be a pretty positive, or the probability of a positive review is pretty high, because my prior probability was that it was quite high, and then the posterior is even higher.
Jacob, there's
Yes.
a question in the chat asking, like, how do you determine this parameter for the prior?
Oh, like how do you pick this?
Yes, yes.
Right, so this is going to be based on like your prior beliefs and experience. So you want to kind of pick something where the shape matches what you believe about like how sort of likely reviews are to be kind of like positive or negative. So if you, well, I guess before I answer that question, let's just show what this looks like. The 100. So this one, you were like super confident that that most reviews would be negative, but then you actually saw 5 reviews, and that contradicted your belief so strongly that you've actually kind of like qualitatively moved things a bit to the right, but still not a ton. So yeah, to answer your question, you kind of want to pick something whose shape kind of matches what you might believe. So, you know, maybe something that I would believe is that most reviews are either like mostly positive or mostly negative. So actually none of these had that shape, but let's try to make something with that shape. Apparently I can't make something with that shape without, oh no, I can, okay. It just gets sad, but the graph still exists. So ignore the error message. But this is what a beta of 0.5 prior would look like, where things tend to be either like mostly positive or mostly negative. There's not that many things in between. But maybe this isn't great because this sort of suggests that positive and negative are about equally likely. So maybe I want to fix that. So let's try to play around with the numbers a little bit. Let's make this, oh no, that was the wrong way. That made things mostly negative. Okay, so maybe this is like, maybe this kind of matches at least what I personally believe which is that most products either get mostly positive reviews or mostly negative reviews. Mostly positive is more likely. So I've come up with this prior distribution that kind of puts like more of its mass on mostly positive reviews, not that much mass on stuff in the middle, most of its mass on mostly negative review, or a little bit of its mass on mostly negative reviews. And I'm not saying this is a prior you should personally use. I think it kind of depends on what you believe about the problem. But this is kind of like the sort of exercise you'd go through to pick these parameters, is like, I would probably just graph stuff and look at what the graph shows and sort of think about whether that graph kind of corresponds to what I actually believe. Does that answer your question? Oh, I can't actually see.
Yes.
Yeah, okay. Oh, actually, oh, I found the chat again. Okay, apparently I can see the chat.
Professor, can I follow up on that actually?
Yeah.
Is it always based on your belief then? Is there no quantitative way of arriving to the parameters?
So there's a few ways of trying to get at the parameters in a more rigorous way. One is one is something you would call elicitation, where I would try to talk to like some domain expert who's actually like had a lot of experience and try to figure out like how frequently they've seen different things and kind of use that to build a prior. Another is I could actually try to get the prior from past data. So actually, with Amazon, we don't have to guess at what the likelihood of these different probabilities is, because there's just like, billions of, well, not billions of products, there's millions of products probably on Amazon. And so you actually have a pretty good idea of what the overall probability distribution is of different theta values. So in this case, you could actually do it pretty objectively if you were Amazon. And there's a few other ways of trying to do it in a slightly more objective way. There's this entire area of research called objective Bayes, although it doesn't, it's not completely satisfying, but you can actually, for instance, come up with choices of priors that have good frequentist properties, in the sense that they kind of are like min-max optimal over some family of distributions. And so that's sometimes another way of doing that. And you get things, you could look up like a thing called a Jeffreys prior, which is related to that. So there's a few ways to try to do this in more principled ways, but I would think of it as like you're sort of a modeler and you're trying to kind of apply whatever domain knowledge you have or can obtain. And probably the best way to do that is either to find historical data or to talk to an expert.
Okay, thank you.
Yep. Cool. Any other questions about these kind of priors and posteriors?
I had a quick question.
Yep.
I was wondering, so it seems like when your prior has like particularly large like alpha and beta values, or like RNS values, then if you'd want to like shift that prior, you need to make more observations. So is it better to start with like a vague initial belief, or like a relatively like small initial belief, or like small values for alpha, like RNS, or is it, if you feel like you have a more precise prior, should you start with that?
Yeah, I would probably in practice use pretty small values of RNS. As you noted, if I use like RNS equal to 50, I'm implicitly saying that I'm very confident before I've seen any data at all. And that seems like probably a bad idea, since it means I'm not going to be very responsive to the data I see. And also it's like not clear where that confidence comes from. So I think in practice, you tend to want to use, yeah, like you said, fairly small values of RNS.
Thank you so much.
Yep. you could also do this for, say, continuous data. So let's imagine that I'm trying to figure out the average height of people in North America, say. And so I have, let's say I have like 100 random people that I've surveyed in North America, and I have their heights. So in that case, this will be the data. And so these heights are actually real numbers. Well, they're positive real numbers. And let's say theta is some sort of average height. And this actually isn't enough to specify a probability distribution yet. So I actually need to say like what is, say, some specific x. Let's just say x1 given theta. And in this case, maybe we could say it's Gaussian. With mean theta. So that would mean it's proportional to e to the minus 1/2 x1 minus theta squared. And maybe we should include a standard deviation as well. And for now, let's just suppose sigma is somehow magically known. But in practice, sigma and theta would both be unknown things that we would need to estimate. But this would be an example of a sort of continuous problem where we say, okay, let's suppose we have a bunch of heights. We'll assume that they're Gaussian distributed. Now I want to infer the average height. And so I need some sort of P of theta prior if I want to take the Bayesian route. So we could imagine that this is also Gaussian. Let's say with some other standard deviation, sigma 2, and some, oops. So this is a prior over theta, and some unknown mean mu. So that's like a potential prior you could use, but we could like have other priors as well. But you could sort of do all of the same machinery with this sort of prior and posterior, and we won't, like, in some sense the algebra isn't the point, because actually it's good to be familiar with the algebra, but you can also kind of have a computer do the algebra for you most of the time. But let's just like see some kind of brief demos of what this might look like as well. So let's go back to the Jupyter demo.
Oh, Jacob, I have a really quick question.
Yep.
So when you did like probability of x1 given theta, you said it's proportional to like -1/2 sigma squared, like x1 minus theta squared. So do you mean that theta in that case is the mean? If it is a Gaussian?
Yeah, so theta is like the average height. So it would be the mean of the Gaussian.
Oh, okay. But if you do like probability of theta, then you assume a different mean, which is mu.
Yeah, so that would be like, let's suppose I'm like, well, I think the average height is probably around 5'10". So then mu would be 5'10", because that's my like the mean, the like prior mean that I have for the actual average height. But then like theta, so like mu is like my prior belief about the average height, and theta is the actual average height. So maybe like think of mu as like your sort of guess as to what the average would be, which I guess in this case I'm guessing that it's like 5'10", but then I want to actually like refine that with the actual data I have. Does that make sense?
Oh, okay. So theta is unknown, but mu is known.
Yeah, mu is known, but theta is unknown. Yeah, good question.
Okay, got it. Thank you.
So let's see. So in this case, I'm actually not sure whether I get to change. Oh, yes, I do. Okay, cool. So in this case, this is like, so let's fix this to like something in inches. So let's suppose that this is going to be my prior mean. So if I thought 5'10", I should say it's that many inches, and like, you know, how off might I be? I don't know. I could imagine it could be like, I guess I wouldn't be that surprised if it was like 5'7". I wouldn't be that surprised if it was 5'11". I'd be like kind of surprised if it was 6 feet or 5'6". So this makes me believe that maybe I should have picked 5'9" as my prior, and we can have a standard deviation of like 2. Okay, so what happened? My prior was sitting around 69 inches, this yellow thing, which is 5'9", and it has, you know, a decent amount of uncertainty. My posterior says 40 inches. Why does it say 40 inches? Oh, because I had one observation, and my one observation was someone who is 11 inches tall. So that's probably not like a good observation. Let's suppose I observe someone who's 5'6", who's 5'5". I observe someone who's 6 feet tall, and someone who's 5'11". Okay, and then I get this as my posterior. So I kind of updated slightly downwards because the average height was a little bit less than 5'9". But the interesting things, I've kind of like concentrated my uncertainty more. Like the posterior is narrower than the prior because I've like gotten this extra information about people's height, and so now I should be less uncertain. So that's just an example of how things might work out in another case, in this sort of Gaussian case. Are there questions about that? So the first point I want to make is I want to come back to decisions. Right, so I guess this doesn't have that much to do with the height question, but for the product decision question, I need to actually choose a product to buy. And so there's a few ways to go about this. So if we want to be sort of really do things using our whole decision theoretic framework, what would we do? So we would basically define a loss function. That is, what do so the loss function is sort of like how bad is it to, or good is it to buy a product at different values of theta. And then I would kind of minimize my expected loss with respect to the posterior. And so that would be the way to kind of do this under the standard kind of Bayesian decision theory risk framework. And so we could do that. We need to think about our loss function. But sometimes like there's not a super clear loss function lying around. And I just want a way of kind of summarizing my uncertainty into a few small numbers. So another thing I could do is provide some way of summarizing P of theta, and then we could decide based on that. So I want to talk about this. It's maybe a little more heuristic than actually going with the loss function, but also in many applications, we will just want a nice way of summarizing our posterior, even aside from any decision we want to make. Sorry, this should be P of theta given X, because we care about the posterior. And so there's a few ways of doing this. One is called, one is we could take the posterior mean. So basically take the expectation of theta given X. And so basically that would be summarizing this kind of entire distribution by its mean value. The other thing we could do is we could take the posterior mode, meaning the most likely value. So that would be kind of here, right? Because this is the top. And this is also called the maximum a posteriori value, or the map value. So you can think of map as kind of an alternative to MLE. MLE gives you the thing that is the most likely value of X, or sorry, that makes the X the most likely, whereas MAP gives you the most likely value of theta. And so that's still not kind of conveying the overall uncertainty, but it's kind of a nice like single value summary, is to just say what's the single most likely value of theta. So that's what the map is. Those are just two nice ways of summarizing distributions that I think it's helpful to keep in mind. So that was that. Oh, and sorry, one other thing is this posterior mean has another name, which is, it's sometimes called the MLSE, which stands for the minimum minimum least squared error. No, the M has to stand for something else. Anyways, the reason for that is if you were trying to guess the parameter for theta and you wanted to minimize the squared distance, the expected squared distance from your guess and the truth, you would pick the mean. Oh, minimum least squares estimator. Thank you. Yes. This is the minimum least squares estimator. So I wouldn't worry too much about these fancy names, but it's kind of like, it's useful to just kind of know that they exist, so that if you see these acronyms in other places, you'll know where they come from. The A stands for A. So MAP is maximum a posteriori, or a posteriori. And I think it's basically just Latin for the maximum I don't know what a posteriori means in Latin, but I think it's something like from the posterior. Yeah. So that's just some terminology, and these are kind of like useful, like I said, useful kind of single numbers you could use to summarize the distribution. Okay. So any questions on any of this? So then one other brief point is computation. So we'll get to this more later, but so far I only have done, let's see, what did I want to say? So far, like I've only used things with like nice closed forms, right? We use this beta distribution or this Gaussian distribution where we can work everything out algebraically. But what if like my prior was just like, you know, some random distribution? Or I don't know, it doesn't even have to be that ugly, but what if it's just like a semicircle or something, like something that isn't like super nice algebraically? Then what do I do? Well, then we can't do this all via algebra. But, you know, at least mathematically, it's still clear what to do. It's just we have to take these kind of complicated sums and integrals. But, you know, we're not just statisticians, we're also computer scientists. So we can do this if we design the right algorithms. And so there's this entire area of work called approximate inference, or also inference via sampling. And this tells us how to kind of handle even these more complicated cases. So we'll get to this in lecture 8, I believe. But that's something to just kind of look ahead to, that there's actually algorithms behind this. So the last thing I want to do is I want to revisit this height example that we saw earlier. So I was saying if we want these heights, we could have this sort of Gaussian distribution. So far, this has all been made up data. So I just want to kind of show you some real data. So this is data collected by someone named Galton. So I'll make this available for you as well. But he sort of collected height. It included like parents and children, but we're not going to be super worried about that. But he just collected height from a bunch of people. And so here's kind of the histogram. Oh, I forgot to share the screen. Okay, so this is this data, this Galton data. So here's this sort of histogram, and I mean, it kind of like, maybe you could argue that it like at least looks kind of bell-shaped, but to me it doesn't look particularly Gaussian. It's kind of like a little bit too spread out, and there's also kind of like these two peaks, like one at 65 inches and one at 70 inches. So can anyone think of a reason why height would not be particularly Gaussian? Okay, so a few good points. So you can't have a negative height. That's true. So it won't be exactly Gaussian. You could just have this from a small sample size. I think Thomas hit the nail on the head, though. So there's male and female populations, and men and women have pretty different average heights. In fact, they differ by about 5 inches, which you can see are these two peaks. So if I split into if I split this histogram based on gender, then actually I get these, I sort of see these more clearly. So I can see things that look somewhat more Gaussian and that are sort of more unimodal, aside, from some sort of finite sample noise. So it turns out, I mean, in general, like the world isn't Gaussian. The world has a lot of complex structure in it. Although often once you've sort of found the structure, then the remaining variation might look more Gaussian. Not always, but sometimes. So we'll kind of get into this more next time with graphical models, but basically we're going to want ways of specifying more complicated distributions than the ones that we just saw today. And so we're going to define a kind of general language for how to specify those. And we're talking about things like, say, mixtures of Gaussians, where you have multiple Gaussian populations, or even more complex things like time varying data. So I think that's a good stopping point.